Hey, welcome back to another Toolbox Tech Talk.
You will start the way that looks supernova. In the nighttime, hit my hotline. Sharing secrets, you wish really was part your life.
Yeah, it's that time of the week again. It's a Sunday, 1 o'clock here in sunny Melbourne, I think, looking out through my rather tinted glass windows. Yeah, I think that's the go. Hey, good to have you all back. And hey, Scotty, Raymond, Charles, we've got the crew on board again. Love to see those friendly faces. And Martin, g'day Martin. Hey, I think I've got you all there. So today, kind of a packed full one. I've got a bit of, as you probably saw in the DMs, I'm doing something on earth fault detection. Not the type that cracks the earth open, but kind of there. Hey, Gian, you're a regular too. Great to see you from Sydney. And I've got a few kind of curly ones I've thrown in there as well, just for fun. So, yeah, thanks for turning up to another Toolbox Tech Talk Live. And I'll just fade the music. There we go. Oh, I think I overdid the smoke machine today. Makes for a good background, eh? Don't you like the little disco lights? Yeah. That's why you turn up to watch this. Someone said, oh, you need to talk to that tech guru, the guy with the gold chain. I love that. I'm gold chain DJ now for tech questions. Yeah, John, it's real plastic. Nothing fake about me. It really goes well when I go to conferences. Everyone can find me. You know, I'm not a very big guy, but I shine, I glint. You get to say the guy with the gold chain. Though I have awarded a few people the honorary award of DJ Glenmo, and there's a few other gold chainers out there like Dave Petrie. Someone once came up to me and said, hey, there's a big dude. He's got a gold chain on. I think he's trying to compete with you. Yeah, no, that was just Dave, an award winner. So there's also Thomas from New Zealand. He got the gold chain as well. They both have done an excellent job of helping promote good safety standards in New Zealand, where I've been running courses under the auspices of Ideal Electrical at their various branches around New Zealand. So that's been an amazing kind of relationship, and really appreciate their support. So today, just a usual bit of news. As you know, Solar Cutters, which I'm a member of and a big fan of, doing their road shows at the moment all over Australia, too many places to mention. So check out solarcutters.com.au if you want to go to a roadshow and get some of those valuable CPD points that you need if you're a SAA accredited store in Australia, or if you just want to hang with the crew. They really do some fun things. In fact, they literally do some fun things. They have a whole gamify session usually as part of their show. Also, of course, there's the, what are we looking here? The just going to get the right screen up here. We've got the the Smart Energy Expo coming up very shortly on the 9th and 10th of April. And I did mention my birthday was the 8th, and I've already had someone offer me a present. That's kind of cool. I wasn't fishing. Sorry, Charles, I wasn't fishing. But there you go. And g'day, Steve/Angie. I think you first started, or your wife, I think it was, referring to me as Glenn Gold Chain. I like that one. That's kind of fun. And hey, John, from the sunniest part of New Zealand. Yep. Yeah, beautiful Nelson, or the top end of the South Island. A beautiful place all over. I'm a Kiwi, of course, for the first 26 years of my life. Living and growing up in beautiful New Zealand, but I go back there a lot, mostly to run training courses. So what else? I kind of got something a bit fun's happened to me recently. I think I'm the last person in the tech world to discover 3D printing. And I've got a mate here who's a real expert on it. And look, we're printing live right now. So we're printing out a range of things, some tools, and even a little figurine for one of my kids, a little Roblox figurine. I love the way you can watch it live on the app while it's printing. So, yeah, that's kind of... And you might actually get to see a video about unboxing the Chidi Plus 4, because I did a little unboxing video with my friend Rez, who's a bit of an amazing polymath and 3D printing one of his many skills. Anyway, so that's just kind of some fun stuff that I've been doing. And if I kind of get my screens back again, let's dive into earth fault detection. Now, as always, please feel free to ask questions in the chat and even by email afterwards. I'm going to put my email in there again. Most of my Toolbox Tech Talks lately have been as a result of people sending me questions in by email. And shout out to John from New Zealand. John, this is all about earth fault detection and the requirement, particularly for MPPTs. So we'll be covering that today. Yeah, so feel free to throw those questions into the chat and I'll just pause occasionally to check them out. All right, so let's dive into earth fault detection. Did you like the little promo I did for it with the earth cracking open? I'm trying to be a bit super literal there, and that's what came up. So here we are, earth fault detection. Let's start with something I've actually shown this once before, but for those who haven't seen it, why is it important and why do we require equal potential bonding of PV arrays that are over 120 volts? It all comes down to things going wrong in the past. Now, this is a case study from 2010. Now, prior to the 2012 edition of 5033, the PV array standard, there was no requirement for equal potential bonding of the conductive parts of a PV module or even the array frame itself. And systems were installed quite happily with no bonding at all on any conductive parts on the PV side. So this is a case study of what can happen under that scenario, and it's one of the contributing factors to why we required equal potential bonding of array frames. I can see Simon says we've got a Snapmaker Artisan 3D printing laser and CNC. Oh my God, you've got the bells and whistles. yeah, that is the bells and whistles. And I think my friend Rez is actually just buying a Snapmaker at the moment. So I guess I'll get to see one. They're pretty expensive, but yeah, nice. So coming back to the case study here, this was a transformerless, or actually two transformerless inverters. That means there's no galvanic separation between the AC and DC side, which is basically every inverter these days. Every solar inverter is transformerless, mainly because of efficiency, cost and weight. So we've moved away from galvanic isolated transformer-based solar inverters. Now the customer got the system installed and it was quite a big system for its day. Believe it or not, 2 kilowatts times 2, so it was basically 4 kilowatts over 2 inverters. It was a big system in 2010 and it would earn some big dollars in New South Wales with their 60-cent feed-in tariff on gross. Now this is a kind of an important detail. It was grossly metered. So in New South Wales at the time when that very, very generous feed-in tariff was around, you could export all of your solar, even if you're using power, and sell it at 60 cents and then buy back cheap grid power at maybe 30 or so. So people were putting in big systems and actually getting really good returns on their investment. But the customer, after having this system installed, noticed their bill went up sixfold. Yeah. Sixfold. Can you imagine the look on their face when they got their bill? Their bill was normally $200. I think it was a quarter, so they were a very low energy user, and it went to $1,200. They just about fell off their chair. So the customer complained and they did actually notice at the time that one of the inverters had a red light on it and it was kind of warm to touch day and night. So the installation company, and I imagine it was probably, winter time, often faults are done at the end of the day when you've done all your real work. You rush around and do quick swap outs of faulty inverters. So they swapped out an inverter without testing it because it was dark. Same problem came back the next day. The customer thought maybe it's the electricity's meter, maybe the meter's faulty and it's recording export as import and something's wrong with the metering. So they contacted their electricity distributor and the distributor sent out a technician who analysed the system. Now this is the configuration of this particular system: 2 inverters, 2 PV arrays, and they're only 2 kilowatts. So relatively small system, and he noticed that the gross meter was showing consumption. Now gross meters should only measure export from the inverter, nothing else. So that means power was coming in on the gross meter and going to the inverters. Now something is very wrong, okay? Something is very wrong at this point. The customer, as I said, their bill went up massively. They noticed there was a fault light on the inverter. It was hot to touch, one of the inverters, night and day, and there were no units being exported. And the customer rang the installer and advised the new inverter was getting hot, just like the previous one. So nothing was done with the second one. The inspection from the utility confirmed all these details, and they noticed that it was consuming 66 kilowatt hours per day. The inverter was consuming 66 kilowatt hours per day doing nothing. And there was open circuit DC voltage on each array, as expected, was correct. So the open circuit voltage on the PV was correct when tested in isolation, and the AC voltage was correct when tested. So some of this looks okay until you start putting a current clamp around the cables. And what they discovered, now this is using just a tong tester, an AC tong tester, so not DC current, AC current measuring here. They were seeing 13 amps on the active going into inverter number 2, and on the DC cables going to the roof, they saw 2 amps AC on the positive and 11 amps AC on the negative. There shouldn't be any AC up there, and it was flowing through an accidental bond to the roof, basically the screws that attach the mounting system to the roof, and then there was one of those solar hot water tanks on the roof with a heating element, and therefore it had a bonding earth, a protective earth, on the hot water service, and that was providing a return path back to the main switchboard to the earth bar. So there was 13 amps flowing through the earth conductor. Whoa, 24/7. What was the reason? So the brave technician got up onto the roof. I'm saying brave because this is very dangerous, and discovered that there were some big holes in the roof where the plug and sockets had blown the metal away from the corrugations. And it was in a rather close proximity to the ocean. Not quite sure how close, but salt spray or salt mist would have definitely been an issue. And they were concerned that it was probably due to salt-rich air causing some corrosion of those connecting parts. So the issue really was not just a single point of failure, it was multiple points of failure. So that tells me it's not just a one-off accident. In fact, all the plugs showed some signs of rust, and of course these are live DC. Now remember, the inverter is transformerless, so if you connect the positive or the negative of a PV array and you have a transformerless inverter, you're going to get reverse fault current flowing from the grid side through that inverter. Yes, ouchie, ouchie, says Ray, indeed. So the upshot of it was, surprisingly, the overcurrent protection on the AC side didn't trip because it was a 16 amp breaker, which was correctly sized, but the fault current was only 13 amps AC because of the long path that it had to pass through to get back to the main switchboard. And it was assumed that possibly the problem was that the PV plugs weren't fully tightened. So there's a compression gland on the back of PV modules, and that needs to be, well, it should be done in the factory, but if you've made up any connections, then you've got to make sure those compression glands fully seal around the cable. It's the right size for the cable as well, because there's different size DC PV array cables. And also, if you haven't pushed home the plug and socket till it goes click, that magical click sound means that the O-ring is actually fully sealed, you're going to have moisture ingress. And no equal potential bonding on the array meant that even when there was a slight leakage, the inverter couldn't detect it because it couldn't find a solid earth resistance point. So it wasn't until it touched onto the roof itself that it triggered this. And that's what we call a bolted fault. A bolted fault is when you get a very, very good connection to earth, and generally inverters will fail at that point. They are actually tested for earth leakage. IEC 62109 Part 1 requires at least 300 milliamps of earth leakage to be detectable and interruptible. But over 300 milliamps, all bets are off. And it generally means that it takes out the semiconductors internally. They go short circuit. It often welds or destroys the grid protection relays, and they go short circuit. And now you just basically got a wire that effectively passes through the inverter, passes AC straight through back to your PV inputs. So yeah, pretty scary. Now there's another aspect to this too, which is Back before 2010, there was some murmurs that there's another reason that you should equal potential bond a PV array frame, not just for earth fault detection, but touch potential when you're using transformerless inverters, touch potential on the DC side, including the module frame. Now, this kind of flummoxed me. I didn't quite understand it, but Dr. Martina Calais from Murdoch University in WA, she's a senior lecturer there. She'd actually done some thinking about this, and she knows all about power electronics. And she goes, well, actually, it's quite normal for a certain amount, approximately up to half grid voltage, to appear on the module's frames. Now, when I say a half grid voltage, so let's say half of 240, 120 volts or so, it's a rather low leakage via capacitive coupling. So it's not like you've directly connected the module frames to the grid. You're getting some capacitive coupling because of the high frequency switching of the inverter, switching around sort of the 18 kilohertz mark, and the module frame itself and the cells act like two parts of a capacitor, and the EVA in between is the dielectric. So you actually have some capacitance naturally in a PV module, and when you're building a system that's 2 or 3 kilowatts, that capacitor gets up to quite a few nanofarads, and so it will pass a small leakage current at up to 120 volts, up to half grid voltage. Now, the risk factor there is it's unlikely to cause any electric shock danger, but certainly touch potential. Well, it is an electric shock, but it's not electrocution, and you might get a fright. So say the homeowner's cleaning their roof and touch the modules, they may just get zip and fall off the roof. So what happened in 2010 was this very thing happened. So it wasn't someone falling off the roof. It was a young child who was playing in the back garden, and they touched a metal ladder that was leaning against the gutter, a metal roof, and the roof had a PV array, and it wasn't equal potential bonding because it wasn't required back in 2010. And they got a small touch potential, enough for them to scream. The parents went and confirmed it. Yes, the ladder was kind of giving them a little shock. The Office of Electrical Safety in Queensland got involved, and they inspected it. They found there was no fault in the system, but there was definitely voltage coming off the module frames. Now, that triggered our requirement for introducing equal potential bonding of all conductive parts of a PV array. Initially, it was just the module frames and the rail to which the cables were attached. That was 2012. But then we upgraded that in 2014, if I'm correct from my memory, to all of the conductive parts of the PV array, including both rails. So, yeah, and that takes away that small potential, that touch potential, and basically makes it safer. So I actually used my secretary, ChatGPT, just to summarise this problem. So for those who are really interested, you can always go back and freeze frame this slide and have a good read. And it explains capacitive coupling and why having no galvanic isolation in an inverter will lead to that parasitic capacitance, giving a measurable voltage. And the mitigation, of course, is earthing or grounding of the conductive parts of the array. So there you go. So that's a little bit of a summary, and I've credited Dr. Martina Calais as the person who brought this to my attention, in fact, the committee as well. So there you go. We just get better at safety as time goes by. I see Charles says, would an RCD on the inverter AC detect this? Yes, though it's not. In fact, back in 2010, and in fact up to more recent versions of the inverter standard, you were actually not required or even encouraged not to put an RCD between the inverter and the main switch inverter supply because of potential false tripping and parallel paths with load circuits. I need to draw all this out to sort of explain it, but yeah, we weren't actually required to do that. In fact, I think it's the opposite. We're required not to do it. But that's all changed. Now you have to follow manufacturer's recommendations, and if they require an RCD of a certain type, typically type B, you do need to provide one. So yeah, that's definitely changed, Charles. And you can use an RCD in lieu of mechanical protection now on the output of an inverter. Yes, so John, John's in New Zealand, and so New Zealand's about to give birth to the latest version of the standards, but they're still operating as John is under the New Zealand Electricity Regs 2010, which mandates the old version of 5033, which only required the bonding of the array modules, conductor parts of the modules, and the array frame to which the cables are attached. It's the later versions of 5033 that said, and both rails, or all parts. For micros, yes, same for micros, because they actually bring AC up onto the roof, and so providing a bonding point for the micros. Remember, they're still an inverter, so they still have that potential to create a touch risk for touching the PV modules. Even if they're just tiny inverters, there's still that capacitive coupling. And many micros actually provide a bonding point on the micro itself. But I noticed that with the Enphase, the IQs 6 and 7, I think, have gone for double insulation, so there's no conductive parts on the micro itself, so you'd probably have to bring up an independent earth to bond the module frames and modules themselves. Yeah, so where are we at? Okay, so let's just dive into some of the clauses now. And what I've done, I've sort of gone back in time to the 2012 edition, particularly for the Kiwis that are still operating under the standard. And it starts with earth fault alarm requirements. So they've been around since the 2012 edition. Currently the referenced cited version in New Zealand, long since superseded in Australia. So as it says, in systems where the PV array is operating at LV, and LV is defined in 3000 as above 120 volts DC, so anything over 120 volts DC, an earth fault alarm system shall be installed. So shall means mandatory to comply. On an earth fault, it causes an action to be initiated to correct the earth fault. So what does that mean? Well, probably an alarm. The alarm is to continue repeating its operation at least hourly intervals until the fault is corrected. So until the fault's corrected. Or it might be the alarm might be visual. So it actually gives some wonderful ways that the alarm can be transmitted to the system owner or operating staff, such as fax. My gosh, I just got a fax from my inverter saying there's an earth fault. SMS is probably also still a valid option or similar. Now, these days it'll be via email usually, but also on site. It's best practice, even back then, to have a local indication. So that's the 2012 edition. We jumped through to the 2014 edition. Additionally, they've specifically mentioned PCE charge controllers, so often called regulators, things like maximum power point tracking charge controllers that operate with an LV PV array, shall also provide fault detection and alarm. Now that's a big change. So 2014, which is not yet referenced in New Zealand electricity regs, but it's long been referenced in Australia, and we've kept this in all the later versions. Every MPPT or charge controller that's got an array operating at LV, that means over 120 volts DC, is required to have an earth fault alarm. Now, this is one of the most poorly complied with, in my experience, clauses. I mean, I'm not going to, I'll bring up some examples of it in a minute, but I don't want to be too harsh. And this is the 2021 edition, so it's dropped the word LV and said 120 volts, because we actually in 5033 2021 start referring to DVCs, decisive voltage levels. So this is the one time we're still talking about a 120 volt, which is the old ELV, LV transition point. So charge controllers operating with PV arrays over 120 volts shall provide earth fault detection and alarm functions. So is that happening? Very popular products such as Victron's Smart Solar and many other brands do not have this functionality yet. Correct me if I'm wrong, guys, because I'm not a Victron installer these days, but only the RS450s had a earth fault detection function, from my memory, from my belief, which is their big units. They have a 100 and 200 amp output, so, and they also had a 450 volt input, so they can definitely go well into the LV range. So you're connecting a 48 volt, in this case, it can go down to 12 volts. You see the range at the bottom there. 12, 24, 36 or 48 volt battery to an LV array, you've now got a potential of, under fault conditions, having LV turn up on that battery terminal. And that's why it's very important to have earth fault detection. Now, a product like this in Australia sells for about $700, just round figures. To add earth fault detection to that, you have to buy something like this. And this is the wonderful Australian company, AERL. I keep saying this every time I get a chance to, because I'd love to cheer on our innovation. Australia and Stuart Watkinson, who was from Queensland, built the first commercially available MPPTs in the world. Go Australia. We pioneered with, the stump jump plough, the humidity crib, and MPPTs and Wi-Fi, the minor thing. But yeah, so it's an Australian invention. I remember saying to his son, who runs the company now, Peter, I said, geez, must have made a lot off that patent. Nah, didn't have as many lawyers as the other companies. So basically didn't really get any royalties off inventing the MPPT. But there you go. So adding a EarthGuard to a, say for instance, that Victron MPPT would meet the requirements, because you can have an external device to provide that earth fault detection. However, I mean, that's about $700 as well. So the earth fault detection costs nearly as much as the, about the same as the MPPT. It's probably a good reason to look for products that actually have integrated earth fault detection, which, fun fact, AERL build them into their charge controllers, so you don't have to buy the EarthGuard separately. Now, this is possibly a bit of a mea culpa moment for me. Now, I've been having quite a bit of discussion with over the emails with installers about the requirement for inverters connecting to ELV battery systems to have galvanic isolation. That means between the battery and the other ports, the PV port, if there is one, and the AC port, which there will be, which are both LV sourced, there must be galvanic separation. Now, I was looking at the Doye's data sheet, and it said non-separated in the data sheet. And so I was thinking, oh, freaking out. This means all those Doyers being installed out there are really illegal. And this is not a good thing. But then, having quizzed an installer who installs a lot of these, he got the circuit diagram back from Doye, which clearly shows an isolation transformer on the battery side. So, whew, I'm okay now. So this is fine. No problem at all. So you've got a ELV battery, you've got LVAC output, but you have galvanic separation. And why is that important? Well, let me just kind of show the little scenario here. See if I can get my little drawing thing up. I've got to rearrange my desk. Where are we now? Okay. Get my drawing thing up here, and bear with me. And there it is there. Okay. Hopefully that's good. I've got it nice and sharp. Yeah, right. So let's look at this scenario here where we've got an inverter. And of course, just to remind you, its standards now refer to PCE, power conversion equipment, not inverters or charge controllers generally. They'll use a generic term, PCE. So this is the PCE. We've got a PV array here, and this PV array is operating at LV, which can also be described using divisive voltage classifications. So it's DVC, B or C. B is 60 volts to 120 and C is above 120. But as far as the battery standard is concerned, B and C are equivalent to LV as defined in AS/NZS 3000. The battery system here is a nominal 48 volt battery, so it's categorized as DVC-A, which is anything less than or equal to 60 volts DC is DVC-A. These all come from IEC 62109 Part 1, which are definitions for risk based on voltage type, like AC or DC, voltage level, number of volts, and environment, wet, dry, or damp. And so from that matrix, there are different voltage ranges for DVC-A, B, and C, depending on the environment, for instance. And of course, we've got the grid over here. So we've got basically two LV sources here. Now, if there isn't galvanic separation from this battery, then we can have a potential fault that will bring AC or DC onto the terminals of this battery. Now, DVCA is deemed to be non-hazardous, and so single insulation. In many jurisdictions, it's not even licensed electrical work. The hobbyists can be connecting up their 12-volt battery, for instance. But if you've got no galvanic isolation, that can be a killer. In fact, there was a death in Queensland about a decade ago, someone working on their car, and they had a little transformerless 12-volt inverter that was faulty, and they died touching their car battery terminals. I mean, it's sad, and it's true. These things happen. So that's why it's very important to have that galvanic separation between, as I've shown here, between a DVCA battery and the terminals of in the LV ports. So there you go. Now, there are ways of testing if other than getting the manufacturer to provide you with a schematic like this, because often they don't. So thank you, Doyer, for this. There is a way of testing to see if you have galvanic isolation, but beware, you probably want to wear safety glasses and gloves when you do this. So if they claim that it's a separated inverter and you were to connect one of the battery terminals to earth, if the smoke comes out of the inverter, they were lying. If it doesn't, it's all good. Because if you don't have galvanic separation, the moment you earth one of the battery terminals, you'll create a direct bolted fault through the power conversion stages of the inverter. It'll bring AC onto the electrolytic capacitors, which are polarized, of course, and they go big time. And I'm sure Charles has popped a few. Teasing there, Charles. It's quite an event. Reverse polarizing a large electrolytic capacitor. The smoke comes out, which is quite a combustible electrolyte, and really, really bad things happen thereafter. I mean, it actually happened to me, and so I've witnessed it, and I wasn't deliberately doing it. I had a Voltronic inverter. If you've heard of that brand, they're often rebranded all sorts of names. I think this one was branded Giant, and then it was a 48-volt battery. MPP Solar, that's another rebrand of Voltronic, and we connected a power supply onto the battery to charge it up because the battery was running a bit low at the time and there wasn't any solar connected. Now, the power supply that we connected was a switch mode power supply without galvanic isolation, of course. So we inadvertently provided an earth return path to the battery on the Voltronic inverter, and boom, it went bang, big time, and lots of smoke. Now, luckily it didn't catch fire as well because, like I said, the electrolyte is often combustible. So there you go. Just to remind everyone, if you're feeling like asking questions, please throw them into the chat. It's all pretty quiet there at the moment. Now, where's my next slide? Okay, I've got to bring that up. And, okay. All right, so, oops, got the wrong layout there. Should be that one. There we go. So, just to reinforce this from the battery standards perspective, because we've been talking about the inverter standard and the PV array standard, from the battery standard 5139, it makes it very clear that a BESS, now this, of course, the sections 4, 5, and 6, but they all reflect the same wording, except 4, sorry, there's sections 4, 5, and 6. Section 4 is for a pre-assembled integrated BESS with basically inverter and battery integrated into it. So I should bring up that slide so you can actually see what I'm talking about. Is a integrated BESS is a section 4 solution, and this doesn't apply. Why? Why doesn't this clause apply? Because there is no DC battery parts being connected or accessible. They're integrated into the product. So let's take SIG Energy Sage and Store battery modules. I believe that the battery modules internally are something like a 32-volt prismatic cell setup, but they have an a DC-DC converter on each battery module to step it up to whatever the bus voltage is for the inverter. So even though they're nominally DVCA internally, because the whole thing is a complete package, there is no accessible parts that are DVCA. So Section 4 batteries don't have this requirement. I also won't say batteries, BESSes, because they include the inverter. Whereas the Section 5 is you have a separate inverter and a separate battery, And then in that case, and Section 6 as well, a BESS shall not be installed if the pre-assembled battery system has a voltage of DVCA, i.e. less than 60 volts, and is connected to an inverter that does not have at least simple separation. Now, I've had a few people query, what is simple separation? There's reinforced separation and simple separation. Reinforced is like double insulated. Simple separation is single insulated. Typically done by things like in a transformer, it's the varnish on the copper windings is simple separation. That's good enough because it's not providing under normal conditions, not under fault, a direct path from primary to secondary on the transformer. So there you go. And also points out the cabling and installation requirements of the pre-assembled battery system shall be treated as DVC-C, i.e. equivalent to an LV, if a non-separated PCE other than an inverter is installed. So if you're installing, here, this is that reference to MPPT, so if you're installing an MPPT, which is a non-separated MPPT, then you have to treat that as DVCE for all components on the battery side. Yep, so there you go. That's 5139. Okay. 4777 part 1, I'm just trying to get all the angles on earth fault detection and alarm requirements. So now we're up to date with the latest version of 4777 part 1, the installation standard for inverter systems. And it requires that if in a non-separated or functionally earthed energy source, an earth fault can result in potentially hazardous current flow due to the return path provided by the intentional earth connection. So it's basically pointing out what the problem is. What is functionally earthed energy source? So for instance, if you connect the positive or the negative of a battery to earth, that's called functional earthing. And it drops, the second highlighted part there is outlining what the requirements for an earth fault alarm shall be. One of the following types. So this is interesting. It's actually a bit of a softening of the previous one having a alarm that is both communication and audible or visual. Now we just give one of the following types. So it can be remote only, such as email, SMS or similar, or it could just be a local indication. Now, I must admit I'm a little bit disappointed by that clause because local indication is probably more reliable than using email or SMS because things change. People's email addresses change, their phone numbers change, and you may not even have internet on site. So having local indication, I think, is pretty good. You know, it's really best practice, and it should be covered in the commissioning of the system with the installation, with the operator of the system to understand this. The reason I say this is I used to do inspections for the Australian government of systems that received rebates all across Australia. It was the Clean Energy Council had the contract to do that for quite some time, and I visited a school, a little Bronte primary school, very sweet school in Sydney, just near the coast at Bronte, and they had a small system. I think it was only like 2 kilowatts. It was part of the Solar in Schools program, and I went and saw the headmaster, and he took me to see the inverter, and there it was, a lovely bright green sunny boy, high up on the wall, so kids couldn't touch it, 3 meters up the wall, and with a little red light on the front. And I said, "Oh, how long has that red light been on there?" He said, ever since it was installed. I assumed that meant it was working. And I said, "No, it says fault. You can't read it from the ground." But I knew what it meant. So it would never worked. That system, which received government funding and was supposed to be a bastion of renewable energy for school kids to look at, it never worked. How sad. There you go. So coming back to earth fault detection, where local indication is used for earth fault alarm, it shall be an audible or visual signal placed in an area that will be noticed. So that's the point I'm sort of making with that story, that it was in a location that no one would really notice because it's too hard to read the word next to that little red light. So, yeah. All right, now we're coming to the end of today, actually, and I had a few sort of discussions with one of my viewers today, and they sent in a few pictures, and this one got me. He actually was investigating a rather large commercial system that had caught fire, and he took a few pictures, Stephen will be very familiar with this problem, probably. People who haven't done the right thing. That's a gland, but it's for a single conductor, and a rather large one at that. So it's providing no protection from water ingress. And this is, as you can see from the side picture, it meant the inverter, so the isolator adjacent to it caught fire because it just would have filled up with water. So cables are great at becoming drip lines. Water runs down the cable, goes straight in that hole, through the plumbing system, known as conduit, into the isolator and catches fire. So, yeah, that was pretty disastrous. And that's the ABB large inverter. Gee, just check out how many DC inputs that has. And it just basically incinerated the whole thing. So it's still under investigation. How come it sort of went from being just a problem on the roof to a problem that set the whole inverter's connection panel on fire as well. So pretty bad. So there you go. Use proper compression glands that seal. Don't enter from the top, because that's the other fault here. If you look again, that's looking down the roof, so water will run down. You can see all the sediment that's collected. It'll run straight in there with a heavy rain. So you're actually asking water to go in there. It's just terrible. So make sure that any entries to DC isolation or enclosures is on the downward side, properly sealed, and cross your fingers. Of course, you don't have to do this anymore because we can use disconnection points if there is 2 or less parallel strings per MPPT. So actually just having a disconnection point, which is just your plug and sockets, as has always been the case in New Zealand, but has been the case in Australia since the 2021 edition of 5033. So yeah, there you go. All right, well, we've actually come to the end of today's session. I sort of thought there might be a few more questions, but I did have one last comment. I think it is, what is it now? Oh yes, I had a question. I'll just answer this visually from a company that sells products in New Zealand, and they said that an inspector had queried the fact that there was 2 main switches in a solar inverter system. There was a main switch grid and a main switch for the inverter system. And according to 3000, there should be a single point of isolation for all systems. Basically, they didn't understand how standards work. So 3000, even though it's a very important standard, isn't the only one you have to get to grips with. 3000 has as normative references. That means to comply with 3000, you have to comply with the normative standards, the standards that are referenced at the beginning of the preface. And normative to 3000 is 4777 Part 1 and 5033. Now, 4777 Part 1 says all main switches shall be grouped in the main switchboard unless practicable. So A, they don't have to be in the same location, and B, they can be separate switches. They don't actually have to be ganged together, so you've got one point of isolation for the whole installation for all sources. However, in 4777 Part 1 2024, we have kind of made things a bit simpler, which is you need to aggregate. When you've got more than 2 inverters supplying a switchboard, you need a separate aggregation board so that there are no loads connected. All inverters, AC supplies go to that aggregation board, and there is a single submain from the aggregation board to a master main switch inverter systems, plural. So effectively, to shut down a commercial site or any site with more than 2 inverters connected, you're only switching off one switch for all the inverters and one switch for the grid. Though in a very big site, you can have multiple aggregation boards. So you might actually have several locations on that site. So you might have aggregation boards on buildings A, B, and C. They all come back to the main switchboard, and so you've now got inverter systems A, B, and C main switches. The other thing which I should probably cover in a separate Toolbox Tech Talk is the terminology has changed for main switches for inverter systems now. We've got main switch supplementary, main switch alternative, main switch independent, and a few others. So yeah, it's got a little bit more words involved, and that's partly to align with 3000. So we've tried to kind of keep our standards in lockstep in terms of wording. So I think that's actually prompted me to cover labeling again in a bit more detail for another Toolbox Tech Talk. So once again, everyone, please feel free to send in your questions via email. Oh, there goes the smoke machine. And yeah, thanks for watching. Okay, check it.
You wish really was part your life. Basic bullets, with no bullets. Does your wife know you're begging for my notice? Promise you're the same.